In our next section, we're going to begin to look at the details of the PE to CE routing protocols and see specifically how they change their behavior when we're routing over the MPLS Layer 3 network. And first, we're going to be starting here with RIP version 2. Now, I'm not going to be going through a lot of slides here that relate to the protocols. We're mainly just going to be looking at this on the CLI and then talking about what are some of the differences between the regular operation in the global table versus the L3 VPN variations. The ones that have a lot of changes are going to be OSPF and BGP. So in those particular cases, there's some RFCs that you would want to reference if you want more information that talks specifically about those changes. And then when we get to those protocols, we'll look at those in detail. Now, in the case of RIP version 2, this is going to be a fairly straightforward implementation, but there is one caveat that relates directly to L3 VPN that we need to talk about. So if we look at the way that our topology is currently set up, we have two provider edge routers, which are router 7 and router 8, and they are hosting the control plane for their customers, which are router 9 and router 10. Now, when we talk about the details for PE to CE routing, the rest of the Layer 3 VPN design stays the same. So we need to make sure, first off, that we have LDP plus IGP through the core, and we're able to establish a label switch path from router 7's loopback to router 8's loopback. We need to create the VRF. We need to do the VPN v4 peering between router 7 and router 8. We need to actually run the PE to CE protocol and then redistribute it into VPN v4 BGP. So when we are varying the protocol that runs from the provider to the customer, that's the only part of the design that changes. The rest of the core, the rest of the VPN v4 routing, nothing changes there. It's only a change on the edge from the provider to the customer, and then when we redistribute the routing back into the provider network. Now, currently, we are doing BGP routing from router 9 and 10 to router 8. So the first thing that I'm going to do is to remove those configurations, and actually I'm going to remove the configuration of BGP from everyone, so we can see from Scratcher what the exact steps are. So let's get rid of the BGP 9, 10, and 100. 100 was in the core. And we're going to start this again by using RIP version 2. Now, from the customer's point of view, when we're looking at router 9 and router 10, there's nothing special at all about their configuration for routing. So we have just normal routing tables configured in the global routing table. It's only in some very few exceptions we'll see, like in the case of OSPF or in the case of BGP, that the customer is going to have to do anything to modify the routing domain as it relates to MPLS. Now, in terms of RIP version 2, the configuration for RIP would be very straightforward. We would say router RIP, we're running version 2. We have auto summary disabled, and we're enabling RIP on 150.100, which is our loopback, and then 150.5.100. And we'll look at then the show IP RIP database. Okay, we can see that we have those particular links, so all of our connected gig links, which are gig 19 and 79, so those are running RIP version 2, and then also we see we have the loopback is directly connected. We normally would have the automatic summary configured, but we're disabling automatic summarization, so we should be advertising the subnets. If we look at the debug IP RIP, we should see that router 9 starts to send the UDP multicasts that are advertising its updates periodically. So again, there's nothing special at all about the CE configuration for RIP. It's just a very basic, straightforward routing config. Okay, the same would be true on the other side. So if we go to router 10, we're basically going to just take this config and paste it in, and we should start to periodically send the RIP updates to the other end. Now, from the provider side, they have the virtual routing and forwarding instance configured, the VRF. If we look at the show VRF on router 7, in this particular case, the VRF is just called VRF1, and it is configured on interface gig 1.79. So from a basic building of the topology point of view, the next step that we would probably want to do before we actually configure the PE to CE routing is just to make sure that we do have connectivity from the provider to the customer. Or in other words, on router 7, we just want to do a ping inside VRF1 to make sure we can reach 155.179.9. Because if there is some sort of underlying transport problem, like the VLAN is configured wrong or the IP address is wrong, we don't want to be wasting time troubleshooting MPLS when it ends up to be something much simpler. So always test basic connectivity first before we get into any of the upper layer applications. So the same thing is true on router 8. We're going to ping a 151.108.10, but that is going to be inside of the VRF. 155, that should say. Okay, now we have connectivity to the customer, and we also want to make sure that we have connectivity through the core. So let's go ahead and do a trace route from 8 to 7, and we're tracing between the loopbacks. Again, we want to make sure that we are following a label switch path, an LSP end-to-end. This is going to allow us to tunnel the traffic over the core. So right now we can tell on every hop here an MPLS label is being used, so the core should be properly prepped. Whatever IGP routing they're doing, whatever labeling they're doing is correct. We don't care the methodology, we just care the final result, that there is an LSP from 7 to 8 and back. Okay, the next step is that since I disabled BGP, we're going to need to re-enable it. But before we do that, let's turn the PE to CE routing on. Now, in the case of RIP, when we start the RIP process, we go to RIP globally, and then under the RIP process, issue what the particular address family is. So we have address family VRF, in this case 1, which means that there's only one global RIP process. We then specify under that subconfiguration mode what particular routing table are we referring to, which again is different than the OSPF implementation where we have a separate instance of OSPF per VRF. In the case of RIP, we just have one process, and then we have the subsequent processes under that from a configuration hierarchy point of view. Now, once we get under the AF, the configuration is identical to a regular RIP process. So this means that we can just take that same exact config that we had on the other side, which is version 2, the network statement, no auto summary, and just paste this on the provider side, but they're doing it inside of the VRF. If we show run section RIP, we can see it's a pretty straightforward config. The only thing is that we're separating it into a different routing table. Same thing is going to be true on router 7. Now, if we look from the customer side, we should see that we start to receive updates from the other end of the link. Okay, it says previously we ignored a version 1 packet from router 7. That's because RIP was configured, but version 2 was not yet enabled. So we should see when our next periodic update comes in, it should be a version 2 update. If it's not a version 2 update, then we're going to have to change it. So we should see eventually that it receives the update inbound. Now, it may actually not advertise anything because it's only enabled on just the one PE to CE link. But let's see from the provider side, are we actually learning the routes from the customer? If we show IP RIP VRF1 database, show IP RIP database for VRF1, okay, we are learning the routes. So if we show IP route VRF1, we should see that we have the RIP routes installed. The same thing should be true on the other side. Now, the reason that I'm checking the database here in addition to the routing table is, again, there are some cases where the route goes into the database, but then gets hung before it actually goes into the RIB. The simple solution for this is, again, to simply just say clear IP route VRF star, or whatever the VRF name is, VRF1 star. This is going to refresh the table, cause it to re-import and export the routes, and then ultimately we should see that the RIP routes are installed from the particular neighbor. Now, in the case of RIP, this is a periodic update, so we're going to have to wait till the update interval expires, and then the other end sends the update back in. But ultimately, we should see that we're learning the routes. Okay, the next step is that we need to configure the BGP peering, the VPN version 4 peering over the provider network. Now, again, we have a couple different options for this. We could do a full mesh of iBGP, We could do route reflection, or we could do confederation. So the regular BGP rules stay the same. The only thing that we're changing is that we're advertising a different address family. Now in this case, since there's only two edge routers, router 7 and router 8, I'm just going to peer them directly with iBGP, and then we'll do the VPN v4 exchange directly between them. But in other examples, once the topology starts to get a little bit more complicated, then we'll add some route reflection, and we'll see how that's going to affect the path selection when we have multiple routes to different CE devices. So on router 7, we're going to start the BGP process, and I'm going to say no BGP default IPv4 unicast, which again means that when I start the peering, do not automatically negotiate the AFI SAFI 1/1, or in other words, regular IP routing. Because normally when you configure a peer, iOS assumes that you're doing it for the purpose of global routing. Now, it's not necessarily going to hurt anything if 7 and 8 were to do global peering, but in a real design, you typically only activate the AFIs that you actually want to use, because we wouldn't want to exchange routes that never get installed in the table. It's just going to eat up extra control plane resources. So then we're doing our peering. We're doing our peering to 8. And again, we need to make sure to source the update from the loopback, because this is what the next hop value is going to be. Then under the address family, VPN v4, we're going to say the neighbor is activated, and it is going to automatically send extended communities towards them. So again, when we show run BGP, it has that extra statement in there, send the extended communities, but we don't have to add that. It's adding that in there automatically. So same thing on the other side. On router 8, we're going to say under BGP 100, we're peering with router 7 from our loopback, and we'll say no BGP default IPv4 unicast. Okay, also notice here we got a message here, a notification. The notification was the AFI SAFI was not supported. This was because of the order of the config that I did on router 8. I configured the neighbor statement before I issued the no BGP default IPv4 unicast. So router 8 sent an open message saying, I want to negotiate unicast routing with you. Router 7 says, no, I'm not configured for that, so I have to shut the peering down. I send a notification, and that tears down the TCP session. Now, we'll see in this case, they're basically going to flap over and over and over, because the AFI SAFI 2.8, which is VPN v4, is not yet configured on this side. So in other words, they do need to agree on the capabilities negotiation. Otherwise, the peering will not come up. So under VPN v4, we're going to say neighbor 151.77 is going to be activated. Next, if we show BGP, VPN v4 unicast all summary, we should see that we have the peering to the neighbor, which we do. Okay, now we have our very last step, which is going to be to take the routes that came from the customer, and we need to originate VPN v4 routes from them. Or in other words, we need to do redistribution. So under the BGP process, this is going to be normal redistribution, just like any other protocol, but the difference is that it goes under the address family for the VRF. So we're going to redistribute RIP. We go into the RIP process and say under address family IPv4 VRF1, we're going to redistribute BGP 100. Okay, same thing on the other side. So if we look at the show run, include BGP or RIP or address family or redistribute. The full config would be essentially just this. So we're doing mutual redistribution in both directions. Okay, so we'll do that on router 7 as well. Next step is we want to check, were the VPN v4 routes actually generated? So we already had the RIP routes. We checked that in the VRF table. We did redistribution. We now need to see, are we locally generating those routes? So from router 7's point of view, if we look at the show BGP, VPN v4 unicast all for all VRFs, we should see that we have our own local routes that are originated. So for example, the connected link between 7 and 9, we are the local originator. the loopback of router 9, the next hop is router 9, but we are the one that's actually doing the redistribution. And we can see here in the origin code is incomplete because we're doing redistribution. Next, if we look at the specific update, if we show BGP, VPN v4 unicast all, 151.99/32, again, the important points of this are what is the next hop value and what is the label. This is going to be used in the data plane to figure out the actual forwarding. Now, in the control plane, what we care about is the route distinguisher and prefix. We care about the route target value, and then we care about the rest of the BGP attributes. Now, in this case, notice that the metric value for the BGP update is set. The metric value is set to 1. Basically, what this is that the RIP hop count automatically gets encoded as the BGP med value. The advantage of doing this is that we can now redistribute from BGP back into RIP on the other side and then maintain the end-to-end metric if we want it. Now, we don't necessarily have to do this, but the issue is that when we do redistribution, if we show IP RIP database for VRF1, unless we set a seed metric into RIP, it's not going to do the redistribution. Because by default, when we say under the RIP process, we say redistribute BGP 100, unless we give it a hop count to put into the database, it cannot generate the update. So it's the same case as like EHRP. If you redistribute RIP into EHRP, you have to set a metric, otherwise it cannot go into the topology. Now, in the case of RIP, we have two options. We know that we could just go under the RIP process, and we could say when you're doing redistribution of BGP, just set the metric to whatever, 5. Now, if we look at the show IP RIP database for VRF1, we should see now the routes are in there via redistribution, and they have the seed metric of 5. The other option here with L3 VPN is that when we are doing the redistribution into the RIP process, we could say, take the metric as transparent. What this specifically means is that since the BGP med was already encoded from the RIP hop count, if we just take the med and then copy that back into the hop count, the metric now becomes end-to-end. Now, in the only design this would really matter, though, is that if you have multiple links to the provider and you also have multiple links on the back end, so for example, if we had a backdoor link between a router 9 and router 10, and they were directly exchanging RIP version 2 over that, then router 10 is going to say, well, do I want to route on the backdoor link or do I want to route on the MPLS network? In today's networks, that's very common where you might have MPLS as your primary circuit, but then you have internet service as backup, like maybe DMVPN is the backup for L3 VPN. Then you would need to decide one metric over another. In the case of RIP, this is straightforward because you can just set the metric based on the offset list. But we'll see when we get to the other protocols, this design starts to get a little bit more complicated. Like if we're using OSPF for PE to CE routing and we do have a backdoor link, it depends on how we encode the route into the database, whether we're going to choose the MPLS route or the backdoor route. But if we were now to go to router 10 and look at the show IP route RIP, we should see that the hop count was maintained end-to-end, where the route that was originally a hop count of 1 now is a hop count of 2 because the MPLS network counts as transparent. If we were to go to router 9 and to do this, if we were to say under the RIP process for address family IPv4 VRF1, or actually no, we're not under the VRF, we're just under RIP globally, router RIP, to say we want an offset list for all networks, and we'll offset outbound, and we'll offset a metric of 3, and just out all links, clear IP route star. When we look at the other end, we should see now the RIP metric is going to be updated. So it went from a metric of 2 to a metric of 5. This is because we're transparently copying the RIP metric into the BGP med and then copying the BGP med back into the RIP metric. But again, you don't necessarily have to do this. It's just one of the options. But the point being is that you do have to set the seed metric. So either you do it manually, like I'm doing here on router router 7, where we're saying under the RIP process, when we redistribute BGP into it, just set it to have a metric value. In this case, I'm saying 5. On the other side, if we show run section RIP or BGP, I'm saying take whatever the BGP med was and then just copy that back into the RIP update. So beyond that, there's no other special behavior of RIP over L3 VPN. It's just regular, normal RIP routing from the customer point of view. From the provider side point of view, we simply create the global process. We specify what is the VRF, and then any of our options go under the VRF. So things like the version, we can see are specific to that individual routing table. Auto summary, the individual network statements, if we were to do offset list, a distribute list. So all of the features are there. It's just specific to that one routing table as opposed to the global table. Our final verification, of course, is going to be the ultimate data play. So from router 9, if we ping 150.1.10.10, and we source this from 150.199, we should be able to reach it. And if we do a trace route, we should see it should follow a 2 label switch path through the core, the top one being the transport label about the loop access 7 and 8, the bottom one being the VPN label that was generated by VPN v4 BGP.